Hello everyone, I'm Hwang from KAIST. Today, I'm going to talk about Centaur, a chiplet-based hybrid sparse-dense accelerator for personalized recommendations. This work is done with my colleague Taehun Kim, Youngeun Kwon, and Professor Minsoo. First, let me begin with the research scope of this work. Since deep learning became so popular, there have been tons of work on deep learning acceleration, which are primarily focused on accelerating the dense and compute-intensive DNN layers, such as DNNs and RNNs. However, for emerging machine learning application shown in this slide, non-conventional DNN layers are causing a serious bottleneck and limiting performance improvements. In this work, we focus on personalized recommendation models, which were recently discovered with its importance and various applicability in domains such as e-commerce, search engines, and social network services. For this model, sparse embedding layer causes an additional performance bottleneck on the top of dense DNN layers. So, you might wonder, what are sparse embedding layers? Or, more fundamentally, what is an embedding? Embeddings are projection of sparse features into dense vector dimension, most notably represented by the famous word-to-vec approach. From a computer architect's perspective, embeddings can be thought of as a wide vector, and the embedding tables can be treated as a large single-dimensional array of embedding vectors. The problem is, to perform personalized recommendations, the model should store all the embedding vectors for each user and items. Considering how many users or videos are available at YouTube and Netflix, the required memory capacity to store these embedding tables can amount to hundreds of gigabytes, which causes several system-level challenges, which will be discussed later in this presentation. Okay, so let me explain how embeddings are utilized in modern DNN-based recommendation models. The goal of a recommendation model is to predict the preference score between a user and an item. In this example, let's assume we are trying to recommend a movie to a given user. To store the embedding vectors for all the movies and users, this recommendation model is assumed as having two tables. First, the model gathers the corresponding embeddings of 3 movies as well as the user from the 2 embedding tables. Utilizing the gathered embedding vectors, you go through a post-processing stage called feature interaction, the output of which is forwarded to the backend DNN layer for execution, which derives the preference score between the chosen user and the movies. By applying the same process to other movies, we can find out the most preferred movie for this user. So, what are some of the key primitives of embedding layers? The first most important primitive is embedding lookup operation, which is also known as embedding getters. Here, we have a large embedding table with n embeddings. From this large table, we need to gather the target embeddings into a contiguous address space because of the nature of gather operation, the memory access pattern becomes highly sparse and irregular with low locality. The second key primitive is the tensor operation that targets the output of embedding lookups. The tensor operation is intended to algorithmically capture the complex interaction between different embedding features. As shown in this slide, tensor operation is commonly done using an element-wise average operation, which effectively reduces multiple embeddings into a single one. So, the key takeaway is that the key primitives in embedding layers are extremely memory intensive and is therefore sensitive to the available memory bandwidth for embedding getters and reductions. Now that we covered the basics of recommendation models, let me explain the current state-of-the-art practice in deploying personalized recommendation services. This figure provides a high-level overview of a typical recommendation model, which consists of 3 parts: the front-end embedding lookup, and reduction, followed by the backend DNN computation. As I mentioned earlier, the size of embedding tables are in the range of several hundreds of gigabytes, far exceeding physical memory capacity of GPUs or any ML accelerators. So, the only possible option under current ML system is to store the embedding tables inside a capacity-optimized CPU memory. Assuming the embedding tables are all stored in CPU memory, there are two possible implementations. The first design point, which we call hybrid CPU to GPU, utilizes the GPU to execute the compute-intensive DNN layers. One important challenge with hybrid CPU to GPU is that the gathered embedding vectors must be copied from CPU to GPU memory. Because the embedding copies are done over a narrow PCIe communication channel, hybrid CPU to GPU can suffer from significant communication latency overhead. So, another possible design point is to use the CPU exclusively for the entire inference process, overcoming the communication bottleneck of hybrid CPU to GPU. However, the CPU-only approach can suffer from the computation bottleneck because the CPU has much lower compute throughput than GPUs. To address the challenges of sparse embedding layers, our prior work on TensorDIMM proposed a near-memory processing based on solution that conducts the embedding gather operation inside the DIMM directly, which allows the high throughput on-the-fly embedding gather and reduction operation near memory, thereby allowing the overall performance to be improved significantly. However, TensorDIMM is based on a GPU-centric recommendation system, the focus of which is different than our proposed Centaur architecture. Overall, because the CPU-centric system is currently the most popular solution for cloud bandwidth deployment recommendation, the rest of this presentation primarily focuses on CPU only as the baseline system for deployment. So switching gears, let's move on to the workload characterization part of our study, the root cause important performance bottlenecks. We use Facebook's deep learning recommendation model, DLRM in short, to model 6 representative DNN-based recommendation models. As previously discussed, recommendation consists of two key modules. The front-end embedding layers for lookup and the back-end MLP layers. We vary the number of embedding tables, the number of gathers for each table, and the complexity and depth of MLP layers in our characterization study. So, in this slide, we show a breakdown of inference latency as a function of different models and batch sizes, from batch 1 to 128. As clearly shown through our characterization, both embedding layers as well as MLP layers account for majority of execution time of end-to-end recommendation inference, accounting for 80 to 90% latency. Since the performance limiting factor of compute-intensive DNNs are well known, we seek to root cause the reason behind such low performance of embeddings. As such, in this figure, we show the effective throughput of embedding layers, which we quantify by measuring how much vectors are gathered and reduced for each embedding layer. What's interesting is that, while the maximum CPU socket-level memory bandwidth is around 77 GB per second, embedding layers suffer from extremely low bandwidth utility. In particular, recommendationally low batches of 1 to 32, which is probably the most common inference scenario, suffer from very low effective throughput. One of the key reasons behind such low effective throughput in embedding gather and reduce is twofold. First, for low batch sizes, the number of embedding vectors together is only in the range of several kilobytes, which make it challenging to amortize the cost of traversing through various levels in the software stack. For instance, the latency for thread launching, scheduling, and etc. Second, each embedding vector size is only in the order of several hundreds of bytes, but embedding gather operation itself is a highly irregular operation with low locality, making it hard to maximize DRAM row buffer hit rates, and therefore lead to low bandwidth utility. To better highlight the challenges of effectively utilizing memory throughput for embedding layers, here we show the effective throughput of embedding layers when gradually increasing the number of embedding lookups for each table, when increasing the batch size from 1, 4, and all the way to batch 128, while large batch size 128 does a better job of achieving higher effective throughput, low to mid-size batches still suffer from low memory utility, causing a significant performance bottleneck. To address the heterogeneous, sparse and dense compute, and memory limitation of recommendations, we propose to utilize the chiplet-based package-level integration technology for designing end-to-end accelerators. A chiplet is a block of integrated circuitry designed to work with other chiplets to form a larger and more complex chip. A multi-chip module, or MCM designs, can connect multiple of these chiplets using a die-to-die interconnection and assemble them inside a larger monolithic package using advanced packaging technologies. A key reason why we believe MCMs are a great fit for recommendation model is that the algorithm combines a heterogeneous mix of sparse and dense layers. In particular, the sparse embedding layers are closely tied with the CPU architecture because the memory capacity constraint of embedding tables mandate the embedding layers to be conducted over the CPU memory. Given such challenge, we propose to utilize the package-integrated, heterogeneous CPU plus FPGA chiplet to construct an end-to-end accelerator for recommendations. A key benefit of CPU plus FPGA chiplet is that both the CPU and FPGA can directly access the CPU DIMMs using fine-grained load and store operations, reducing overall latency in embedding gather operations. At the same time, the configuration logic inside a FPGA chiplet can be utilized to accelerate the compute-intensive DNA layers, achieving performance improvements. Another important benefit of our chiplet-based accelerator is that it is socket compatible to existing server chassis, which make it easy for cloud data center utilized for recommendation services to employ, as it is minimally intrusive to commodity server racks and therefore the overall TCO optimized data centers. With that, let me present Centaur, our hybrid sparse-dense accelerator for end-to-end recommendation inference. In this work, we utilize Intel's HARP version 2 platform, which integrates the CPU and FPGA chiplets within the same package, allowing the FPGA reconfigurable logic to directly read and write data from the CPU DIMMs, using fine-grained load and store semantics. Utilizing such capability, we implement the heterogeneous, sparse-dense accelerator inside the FPGA reconfiguration logic, where the sparse accelerator complex directly gathers embedding vectors and reduces them over the cache-coherent CPU to FPGA link, the result of which is forwarded to the backend dense accelerator complex in a seamless fashion. Let's now go through some of the low-level operations conducted in each of these accelerator complexes. As I just mentioned, the sparse accelerator is designed for high-throughput embedding vector gathering reductions. Since the embedding table and the sparse index array that contains indices themselves subject for gather operations. The sparse accelerator's operation starts by first copying the CPU side base pointer address information of both the index array and the embedding tables to the FPGA chiplet. Once the base pointer information is available, the FPGA side embedding gather unit is able to address where within the CPU memory address space the index array and embedding table are located. Utilizing this information, the sparse accelerator starts copying the sparse indices from CPU memory to the FPGA side SRAM buffer. Now that the index values are available, The gather unit drives the CPU memory address of embeddings to read, which we utilize to start streaming in the embedding vectors in a high-throughput manner. As depicted in this slide, the gathered embeddings are reduced on the fly within the reduction unit. The final resulting reduced embedding vector, which we forward to the dense accelerator complex for backend DLRM processing. Overall, we carefully designed the embedding gather units to aggressively prefetch the sparse indices such that embedding gather operations are constantly fired off to CPU memory to maximize throughput. So with that, we're done explaining the mechanics of how Centaur improves the effective throughput of sparse embedding layers. The remaining question is, how do we go about accelerating the backend dense DLRM layers? In general, the dense accelerator complex is designed to accelerate two key modules, the feature interaction and the MLP stage. As feature interaction requires the output of bottom MLPs, the dense accelerator first copies the input and weight tensors of bottom MLPs. Once the tensors are copied to the PGA, the GEM unit initiated the bottom MLP computation using the spatial PEs. The output of bottom MLP are sent to the feature interaction unit, which is combined with the reduced embeddings from the sparse accelerators. To conduct the batcher GEM operation, we're modeling the complex interactions. Utilizing the output of feature interaction, the top MLP step is initiated. Again, using the spatial PEs within the GEM unit. Lastly, the final output are post-processed to drive click-through rate final output, which is forwarded to the CPU. Now, I'll explain our evaluation methodology. All the evaluation reported in our study is measured end-to-end over real silicon based on Intel's HARP platform. When discussing the improvement in effective throughput in embedding layers, we compare the result against the baseline CPU-only system, whereas the end-to-end performance is compared against both CPU-only and hybrid CPU-to-GPU. For brevity, in this presentation, we discuss three DLRM models. Two models that are dominated by embedding layers and one that's limited by MLPs. As shown, the high-throughput embedding gather engine helped dramatically improve the effective throughput of embedding gathers by an average 27 times. Compared to the baseline CPU only, the FPGA-side embedding gather unit is designed to aggressively launch embedding loads in a high-throughput manner. A key reason why this is possible is because Centaur does not have to suffer from CPU-side software layer overheads, as all embedding gather operations are orchestrated at the hardware level. So far, we've shown the Centaur's high-throughput gather unit significantly resolved the bottleneck of embeddings. Additionally, the GEM accelerator within the dense accelerator complex helped address the compute limitation of MLPs. As the low effective throughput of embedding gathers are more pronounced during the small batch inputs, Centaur's benefit are more pronounced in batch 1 to 32, achieving an average 9 times speedup. Nonetheless, even for large batch inputs, Centaur's dense accelerator complex still help address the compute limitation of MLPs, achieving an average 4 times speedup. To summarize the presentation, we propose Centaur, the first end-to-end ML accelerator for personalized recommendations. Our solution is a highly practical solution, readily deployable in cloud data centers, as it is package-level integrated MCM design, is minimally intrusive to TCO-optimized data centers. Additionally, we expect the reconfigurability of the FPGA chiplet to enable Centaur to be optimized for alternative recommendation algorithms that employ attention mechanisms.